In this video, we're going to talk about concavity. Let's start with an example of two companies, and we're going to look at their total sales, thousands of dollars, over, it looked like a 5-week period, even though they say 4-week period in the instructions there. So it appears that both companies are doing well. They're both seeing an increase in sales over the 5-week period. But what we're noticing is that company B is on track to outperform company A. And that kind of, you get this sense that it's increasing their sales at a rate. So company B is increasing sales, but at a faster rate than company A. Now, company A has an increase in sales, but the increase is almost kind of slowing down, right? It's almost like they're kind of reaching this point where they're going to like cap out a bit, right? They're not going to probably go beyond a point. At least it looks like that. That matters. That is a measure of concavity. Now, they do dive in a little bit deeper in the textbook, and here I included those tables. So for company A, they just recorded approximately the sales for each week for the first 4 weeks, and same for company B. And then they ask us and complete the rate of change for each of these. So they calculated the first rate of change. Basically, they're just taking the difference in the sales, right? When they're talking about rate of change, right? They're subtracting the sales values. So just so we're clear at what they're doing here, they're looking at those two values. They're doing 5 minus 0, oops, 5 minus 0 over 1 minus 0. And that's where they're getting 5. Okay, so let's do that same rate of change. This time we're going to do 7.1 and 5. Okay, so looking at the difference between 7.1 and 5, that's going to come out to 2.1. And you're dividing by 1, right? Because 2 minus 1 is 1. You're always going to be dividing by 1. So this is going to come out to 2.1. The next one is going to come out to 1.6. And then the next one, 10 minus 8.7 is 1.3. So we're seeing that the rate of change is slowing down. Over here in company B, let's do the subtraction. So this time we're going to do 2 minus 0.5. 2 minus 0.5 is going to come out to 1.5, which we divide by 1. Then 4.5 minus 2 is 2.5. 8 minus 4.5 is 3.5. So this is steadily increasing the rate of change. So what we're seeing is that the rate of change for A is decreasing, but the rate of change for B is increasing. And that is the idea behind concavity. And as you can see, they kind of demonstrate it by showing that the rate of change between these 2 weeks, right, that it has a smaller increase in the rate of change for those 2 weeks. Whereas when we compare here, the rate of change for these 2 weeks, the next couple weeks down there, that's going to have a bigger rate of increase. All right. But what's really going on is it's this idea visually, the graphs are cupping. But the graph for the first one, company A is cupping downward, where for company B, it's cupping upward. All right. And we describe that as concave up and concave down. So by definition, it's the idea that we're looking at the rate of change, but visually we see this kind of cupping idea behind the curve. So the function is concave up if the rate of change is increasing, and concave down if the rate of change is decreasing. When it changes from concave up to concave down, we give a special name. That's called an inflection point. Okay, so let's kind of look further at concavity to understand how that works. So we're going to do an example kind of building, on the same idea they did, where we're going to look at the equation and figure out all of these values. So get a calculator. If you don't have a calculator, go ahead and grab one. And let's get to calculating here. So first thing I want to do is I'd like to look at the graph of this object. So to do that, I'm going to actually go ahead and use Desmos. So I'm going to go ahead and start Desmos here and switch us over so you can see it. All right. Actually, I'll take a second and type it in. I have to attach my keyboard though. Desmos.com. There we go. All right. Here we go. All right. Let's go ahead and enter the equation into Desmos. So we're going to enter h of t equals 144 minus 16t raised to the 2. All right. Now, as it is, I can't really see the graph. All right. And I'm not really worried about that. I'm more interested in getting information from the table. So I hit that little cog button here. Let me just show you. I hit this little cog button right here. And then this button here is the table. And this is going to give me the values I want. I believe they ask us out to 3. So 3 is 0. Okay, cool. So we need those first 4 values. Go ahead and record them into your table. I'm going to go ahead and switch back and do that. So we have at 0, it was 144. At 1, that was 128. 2 is 80. And 3 is 0. Now I could have gotten all of those values just simply by plugging them into the equation, plugging in 0, 1, 2, and 3. Now let's find the rate of change for each of them. So what I'm going to do is I'm going to look at these first 2 ordered pairs right here, okay? And I'm going to subtract the h of t values and then divide it by the subtracted t values, which is always going to be 1, just like in the last example. So 128 minus 144 actually comes out to a -18. 80 minus 128, that comes out to -48. And then 0 minus 80 comes out to -80. So based on this, it looks like the rate of change is decreasing. And that would mean then that the graph is concave down. So it's decreasing in value, which means, that it's concave down. So here's what it kind of looks like, concave down. So the first 2 are examples of concave down. One, though, has the graph increasing, where the other one has the graph decreasing. Concave up, see how it's cupping upwards. One has the graph increasing, one has the graph decreasing. So let's look at this with a graphical example. And let's go ahead and use this graph to figure out concave up, concave down. Okay, so this thing looks like it's concave up to start, right? Traveling along, and then it kind of looks like it switches right about there. It looks like it switches from concave up to concave down. So right here, then, I'm thinking that might be an inflection point. So it looks to me like it's concave up from -infinity up to -1. Then it's like it goes concave down for a while, right? And then it looks like it picks up to being concave up again, like, oh, it's kind of tough to say. Sorry, let me switch back to my highlighter. You know what? I'll go ahead and guess to start concave up again, maybe around 2, just to make it easy on myself. So right around there, I'm going to assume that it's be concave up again. So that means I'm going to use the union symbol and then say from 2 to infinity, it goes concave up. So then it's really only concave down from -1 to 2. And then I have 2 points of inflection or inflection points. Just to comment on that. At x equals -1, and again at x equals 2. I could find the ordered pair, by the way, the y value for those, like I could approximate them, but it's okay. I'm just gonna comment that that appears to be where it looks like it's turning. Okay, so let's look at our toolkit functions and talk about concavity and increasing and decreasing. Now, you have these graphed, and I'd look at those graphs really quick. I'm just going to think of the rough sketches of each of these and not really very detailed. Okay. The constant function is a horizontal line somewhere. So that is neither increasing nor decreasing. Here, I'll put not applicable, NA for not applicable. And it is neither concave up nor concave down. So again, I'm going to put not applicable. I could state neither concave up or concave down, but I'm feeling a little bit lazy. All right. The identity function, that's the f of x equals x. That's the diagonal going right through 0, 0. Again, not increasing. Oh, no, sorry. That is increasing. That's increasing forever. The whole time. Here, I'll even put from -infinity to +infinity. But it isn't concave up or concave down. It has no curvature. Okay. The quadratic, that's the parabola. That looks like the U. And that is increasing from 0 to infinity, but it's decreasing from -infinity to 0. And it's concave up the whole time. All right. Cubic function. So that function looks like the stretched out S. That's how I like to kind of think of it, something like this. So that is increasing the whole time. And here I'm going to use that abbreviation. But it is concave up and concave down 2 different places, right? It actually switches from concave down to concave up. So here I'm going to do concave down first. So it's concave down from -infinity up to 0. And then it switches to concave up from 0 to infinity. Oops, positive infinity, no negative there. All right. Reciprocal function. That's the one that has the 2 separate parts in quadrants 1 and 3. That one is decreasing the whole time. In both quadrants, it's just decreasing in value. It does, however, to have 2 types of concavity. It's concave down in quadrant 3 there, right? So that would be from -infinity to 0. And then concave up from 0 to infinity. Except it's in quadrants 1 and 2. All right. So for this one, it's increasing in quadrant 2. So that's from -infinity to 0. Decreasing from 0 to infinity. And here I'm going to switch to saying CUCD for concave up and concave down. So here, CD, CU. Okay, so concave down. So it's concave. Oh, it's not concave down at all. It's concave up the whole time. Both quadrants, right? But there is a break at 0. So we're going to go ahead and break it up at 0 since technically the function doesn't exist at 0. All right. Cube root. So cube root kind of looks similar to the cubic, except it's on the side. So it's doing this. All right, so that one is increasing the whole time. And it has concave up, it looks like from, it's supposed to cross at 0, 0. So it looks like it's concave up in the bottom quadrant, right? Quadrant 3, so from negative infinity to 0, and then flips or curves upward, switches concave down, I mean, in quadrant 1. So that goes from 0 to infinity. Then the square root, that's like a sideways parabola, but only half of it. That's how I think of that, something like that. It's supposed to be curvier than I just drew it. It is, however, increasing the whole time. And it's concave down the whole time. Oh, have infinity, start from 0 to infinity. Don't include 0 though, right? We don't put brackets there. And it's concave down. Same with concavity, we don't use brackets. Absolute value, that's the V. And that one, it is increasing from 0 to infinity, but decreasing from negative infinity to 0. And it is neither concave up nor concave down. So the minute it loses that curve, it no longer has the concavity. And that's it.